The solubility product constant is a measure of how soluble an insoluble compound is. In Chemistry 1, we talked about insoluble compounds when we talked about aqueous reactions. We had the solubility tables. One of those compounds that was insoluble was silver chloride. We call silver chloride sparingly soluble. So it has a KSP associated with it. What we've been working with for the last two topics, this is the third topic, generating K constants. So these Ks are an equilibrium value. With a solid, what we're looking at is how much will they dissolve. For something like silver chloride, it will dissolve just a little bit, and that just a little bit is the solubility product constant, where we have the concentration of the products, again, in this case the ions, divided by the concentration of the reactants. Now, because the reactants are water and a solid, then the reactants are just one, so the K value is dependent on the concentration of the products. So we have some solubility constants here, and there's a table within the classroom. Solubility constants can be very, very small. For example, we have iron hydroxide, this ferric hydroxide, 4 times 10 to the negative 38th. That means very, very little ion is made from that solid. So when we go to write things like the equations and the solubility product constants, then what we're going to do is we're going to separate these things into their common ions. So here we have silver iodide. Now, iodine is a halogen located right over here. Hopefully you can see my cursor on the periodic table. And because of that, it has a -1 charge. That means my silver also has a +1 charge in order to make this ionic compound be neutral. So this is how we would break up. Now the solubility product expression would then be dependent on the concentration of the products, like this, and I put Cl. So for number 2, we have calcium carbonate. Calcium is a +2, carbonate is a -2. We have one of each when they break up. So the K expression is dependent on the concentration of the products. Number 3, we have magnesium hydroxide. Now in this time, we have our magnesium, and magnesium is a +2. And we have 2 hydroxides. Remember what we do with that stoichiometric coefficient. So the K value will be dependent on the concentration of the magnesium times the concentration of hydroxide squared. Number 4, this is a case we actually have 3 ions here. Now that might not be something that you've seen before, but just use your intuition with some of this. So magnesium is a 2+. I'm going to leave off the aqueous because I'm getting a little bit sloppy. Then I have my ammonium ion, and then I have my phosphate. So that means the K value is going to be dependent on the magnesium times the ammonium times phosphate. So for number 5, we have these 3 ions. Pay attention to these subscripts though. So we have this solid, and it will break into 5 calcium plus 3 phosphate plus a hydroxide. That makes the K expression equal to calcium raised to the 5th power times phosphate raised to the 3rd power times hydroxide. Like with other equilibriums we've seen, we can calculate an X value, a change. Now that's, when we're talking about solubility, the X is called the solubility or the molar solubility. Now that molar solubility is usually expressed in moles per liter, and we can calculate with it. So when we're looking for molar solubility, we're looking at equilibrium concentrations. So here I have the solubility of a calcium fluoride solution or a calcium fluoride solid. This is actually a mineral called fluorite. It's only slightly soluble, and we are going to calculate the solubility product for fluorite. So the solubility product is the K value. K is going to be equal to the concentration of calcium times the concentration of the fluoride squared. And that's because of this stoichiometric coefficient. So here we're told what our concentrations are. So the concentration of calcium is this value here. I'm just going to plug in. And the concentration of fluoride is this value. And I'm going to square it. So I can find the KSP value of this item, and when I put that in the calculator, I get that the KSP is 3.7 times 10 to the negative 11. So see, we can calculate the solubility product. Now we can also calculate concentrations when we're given the solubility product, and that's called the molar solubility. So here we have this copper bromide. And now that's going to dissolve a little bit, and it's copper 1. So we're going to have copper 1 plus bromide minus 1. So the solubility is going to be K equals the concentration of the copper ion times the bromide ion. Now we're told that the KSP is equal to this number. So what are we going to do in order to find these concentrations? Just like with our other equilibriums, we're going to start with some value. We start with none of it, but we do have some of this solid. But remember, solids do not occur in the K expression. We're going to change it by some value X. That happens to be our equilibrium concentrations as well. So I'm going to have X times X is equal to 6.3 times 10 to the negative 9. Remember, X times X is X squared. So when I solve for X, I get 7.9 times 10 to the negative 5, and that's a capital M molarity. So that is this molar solubility of copper bromide. We can calculate the molar solubility of something a little more complicated as well. So here we have calcium hydroxide. Calcium hydroxide will exist in equilibrium with a couple of its ions. So it will break into 1 calcium and 2 hydroxide. Now we're told that the KSP of this equilibrium is 8.0 times 10 to the negative 6. So that's going to be dependent on the equilibrium concentrations of the calcium times the equilibrium concentration of the hydroxide squared. Now let's go back to looking at this as an equilibrium. So because the calcium hydroxide is a solid, we don't look at it as having a concentration. But we do look at these products as having a concentration, and initially they have none. We're going to change the concentration. We're going to change it by some value X. Remember your stoichiometric coefficients, that means that the hydroxide is going to change by some value 2X. So at equilibrium then, the concentration of the calcium will be X, and the concentration of the hydroxide will be 2X. So now we can calculate the molar solubility, which is the X in this equation. So here I have my KSP, and then I have the concentration of calcium, which is going to be represented by X, and the concentration of hydroxide, which will be represented by 2X. Don't forget to square that. So I'm going to simplify this just a minute. So I have x times 2x squared. Well, 2x squared is 4x squared. 4x squared times 4x squared times x is 4x to the third. So then in order to simplify this and solve for x, first I divide both sides by 4. So I get x cubed is equal to 2.0 times 10 to the negative 6. Then I need to take the cube root. If you don't have a cubed root in your calculator, you need to raise this number to the 1/3. So the keystrokes would be, you have your number, and then you should have a raise it or a caret button, raise it to a value. And then in my calculator, I have to put it in parentheses, 1 divided by 3. That's how you take the cubed root if you don't have a cubed root in your calculator. So I find that x is equal to 0.013 capital M molar. So that is the molar solubility of calcium hydroxide. Now the solubility is not always given in molarity. So sometimes you're going to have to convert. It's not a big deal. So here we have lead chromate. Now lead chromate, the solubility of lead chromate is given at 4.3 times 10 to the negative 5 grams per liter. So here you have to convert your grams into moles. So you need to find that molar mass. And I found that 1 mole of lead chromate is 323.19 grams. So when I do that arithmetic, and here my grams are going to cancel, and I'm left with moles per liter, which is what I'm looking for, I get 1.3 times 10 to the negative 7 capital M moles per liter. So we're told the solubility is this value. So the solubility product equilibrium constant is going to be that KSP value. So here, my lead chromate will be dependent on the concentration of the lead and the chromate. And I don't have any additional stoichiometry that I need to worry about. So if KSP is equal to the equilibrium concentrations of lead times the equilibrium concentration of chromate, and this is all a 1-to-1-to-1, I put this solubility value in for each of these because they would each be this x, and I find that the KSP is equal to 1.7 times 10 to the negative 14. Now here we're going to calculate solubility with some, again, more complicated stoichiometry. We're asked to calculate that molar solubility, so we're looking for that x value. We know initially we have some solid. We'll have none of our products. We're going to change that by some concentration. That concentration will be represented by x, and then the chlorine will be represented by 2x. Now that will also happen to be our equilibrium concentrations. So the KSP is going to be dependent on the concentration of that mercury ion times the concentration of that chloride squared. So when I put in the concentrations that I have x, and then I have 2x that is squared. My KSP value was given at 1.1 times 10 to the negative 18. I then need to just solve for x in this case. So I'm going to simplify this. Remember, this part here is 4x squared, and I'm multiplying it by x, so I get 4x to the third. Divide both sides by 4, take the cubed root. I get an x value of 6.5 times 10 to the negative 7, capital M molar. So that is the molar solubility that we're looking for. Now we can also use KSP in order to predict if precipitation will occur. Like with our equilibrium concentrations and equilibrium problems we've had before, at any snapshot in time, we can calculate a Q, a product quotient. So Q is found similarly to KSP. We just use instantaneous molarities instead of our X values. So here we have a magnesium hydroxide. Magnesium hydroxide in seawater is this value of magnesium. And we want to know, will the hydroxide precipitate when enough calcium hydroxide is added to give our concentration of hydroxide? So we need to start with, how is that KSP, what's it dependent on? Well, you find that KSP by taking the concentration of the magnesium times the concentration of the hydroxide squared. So in order to find Q, I'm going to use my instantaneous values and plug them in and solve. So we're told that the concentration of the magnesium is 0.0537. And we are told that the hydroxide is 0.0010. So now it's a matter of solving for Q. When I plug this into my calculator, I get a Q value is 5.37 times 10 to the negative 8. Now this is greater than the KSP value that is given to me. Remember how equilibriums work. When the Q value is greater than the K value, that means we need to shift left in order to reach equilibrium. So there will be a precipitate in this solution. So because Q is greater than K, there will be a precipitate. So let's work another one. Here we have silver chloride. Silver chloride is a generally insoluble compound. It's slightly soluble. And the K value is going to be dependent on the concentration of the silver times the concentration of the chlorine. Now here we're told that we have a 2.0 times 10 to the negative 4 solution of silver nitrate. And we're going to mix it with a 2.0 times 10 to the negative 4 solution of sodium chloride. Now remember, from Chem 1, this is going to be a double displacement reaction. We're going to take and we're going to transpose these cations. So I'm going to make sodium nitrate and silver chloride. Remember, we would identify silver chloride as a precipitate that would come out. So the question is, will it precipitate given these concentrations? So because this will break apart, because compounds of nitrate are soluble and compounds of sodium are soluble, we can call the concentration of the silver this value and the concentration of the chloride this value. So if that's the case, then what we're doing is we're calculating a Q. So I'm going to take my 2.0 times 10 to the negative 4 for each of these values, and I will calculate my Q to be 4.0 times 10 to the negative 8. Now that means, and I need to have my KSP value. So the KSP value is 1.8 times 10 to the negative 10. And if you don't have that, if you aren't given that, there is a table within the classroom, and I'll try to make sure that that's on your quiz as well, or available to you on your quiz. But the KSP is 1.8 times 10 to the negative 8. The Q value is greater than the KSP. Therefore, yes, there will be a precipitate. Now we can also take our QSP value and calculate concentrations that we need. For example, in this example for calcium oxalate, we want to know if the calcium oxalate, or at what concentration of calcium and what concentration of the oxalate must be established before we get a precipitate. Well, you're going to need to know how the calcium oxalate breaks apart, and you need to know the KSP. So the KSP value that I found on the table within the classroom is 2.27 times 10 to the negative 9. So this calcium oxalate is going to break up into 1 calcium and 1 oxalate. That's all that you need to worry about. You don't need to worry about this water. So it's a 1-to-1 relationship. The KSP is going to be dependent on the concentration of the calcium times the concentration of the oxalate. So let's go back to our problem. We're told that the concentration of calcium is this value here. So I'm going to put that value in. And now I can solve for what I don't know. So in order to find the concentration of the oxalate, I take and divide both sides by 2.2 times 10 to the negative 3. And I get an oxalate concentration of 1.03 times 10 to the negative 6 capital M molar. It's at that point that the equilibrium is established and the precipitate will begin to form. Anything greater than that, and you are most assured to have a precipitate. We can have a mixture of compounds and then see which compound is going to precipitate out first. So here we're told we have a silver nitrate gradually added into a solution that contains both potassium iodide and potassium chloride. So you'll need to be able to pick out what might be those insoluble compounds. So we're going to be looking at silver iodide and silver chloride. Now each of these breaks up in a 1-to-1, and that's a 1-to-1 stoichiometric ratio. So that makes everything a little bit easier. You'll need to look up the KSP, and the KSP values that I found in the table in the classroom differ a little bit from what's given in the example answer. So I'm going to go with what I found in the classroom. And I found that the KSP value is 1.5 times 10 to the negative 16. For Ki, and KCl, the KSP is 1.6 times 10 to the negative 10. Now, because we have this 1-to-1 situation here, we know that we're going to be dependent on the concentration of the silver times the concentration of the chlorine. Concentration of the silver, we don't know. Excuse me, I said chlorine, so this one's going to be iodine and this one's going to be chlorine. Now, because these are ionic compounds and they break up completely, we can look directly at the moles that are given. And if we're going to keep this moles, and it does say per liter, so moles per liter, we don't have to worry about converting anything. So for the iodine, our concentration is 0.0010, and for chlorine, we have 0.10. So now we need to solve for the concentration of our silver. And what we're going to do is find at what concentration of silver will the precipitate start to form. So when I do this arithmetic, I get 1.5 times 10 to the negative 13 for the iodine. And for the chlorine solution, or the chlorine compound, I get a concentration of 1.6 times 10 to the negative 7. So because this concentration is so much less, the silver iodide is going to precipitate first. We also have what's called the common ion effect, and that's going to have a direct effect on the solubility. Remember, this is an equilibrium. So when we insert, let's say we're looking at this silver iodide equilibrium. If we insert more iodine, how is that equilibrium going to shift? Well, by increasing the concentration of the iodine, we are shifting to the left towards more precipitate. So we need to be aware of how those ions will shift. So here, if we have cadmium sulfide in a solution of cadmium bromide. So what I'm interested in is the cadmium breaking into the sulfide. Now, again, it's a solid, so we don't look at a concentration of a solid. We're looking at the cadmium and the sulfur. Now, I'm told that we have a 0.010 molar solution of cadmium bromide. Well, that is a soluble compound, so I'm starting with this initial concentration, but no sulfur. Now, I need to shift this by some value x. Since I have no sulfur, I'm going to end up adding x to this side, to the product side. That's going to be my change. So at equilibrium, my cadmium will have 0.010 plus x. So now I can set up my KSP. Remember, KSP is the product constant at equilibrium, and here we're going to be dependent on the concentration of cadmium times the concentration of sulfur, which I just found out to be 0.010 plus x times x, and that equals a numeric value 1.0 times 10 to the negative 28. Just like with our other equilibria, we can look at our initial concentration and compare it to our K value. Because we are greater than 1,000 times different, I can simplify this part of the equation. So now I have 0.010x equals 1.0 times 10 to the negative 28, and I can directly solve for x to be 1.0 times 10 to the negative 26. So that's the molar solubility, that's the x value, of cadmium sulfide in this solution.